Okay, so once again, we're scheduled to finish chapter 9 today. I have a few goals, two sort of main goals, which have smaller sub-goals. And one of them involves a reaction that's peculiar to alkynes. Up until now, we've been looking at reactions of alkynes that are entirely analogous to the reactions of alkenes that we learned. Use, if not identical, at least very similar reagents and very similar types of outcomes. But there's one reaction that, that is special for alkynes, and in particular, terminal alkynes. And we've defined terminal alkynes in a previous class. We said that terminal alkynes are those where the triple bond is at the end, hence the word terminal, of the carbon chain. Or in other words, terminal alkynes will have an alkyne carbon-hydrogen bond. And those are special. That carbon-hydrogen bond is a special reactivity of the type that we don't find with alkenes and we don't find with other types of alkynes. So we need to get to that. And as you can see, the reactivity entails that, this hydrogen is slightly acidic and can be pulled off with a sufficiently strong base. So we'll get to what that base is. And at the beginning, I want to make it very clear what exactly that base is so that we're clear on its structure and we understand what's going on here. And I also want to be very clear on why that is a strong enough base and other apparently obvious choices are not adequate choices for the reaction at hand, for pulling off that proton. So I'm just going to get a little bit into the theory. I found myself sort of going on this, going in this direction pretty strongly in the previous class. Kind of surprised me. I went more so into it than I had in previous semesters, but I think it worked out all right. I think it's good to dwell on that because I really want to make sure that everyone understands what's going on here and why, as opposed to just memorizing a reagent. Once we've made these so-called acetylide ions or terminal alkynate ions, you can call them either. This is called an acetylide ion, an acetylide ion. And no big surprise, right? That "ide" ending, we're used to seeing that with anions, right? Chloride, hydroxide. So nothing out of the ordinary here either. So once you get this acetylide ion, so what? What can you do with it? And the answer is a great many things. We'll learn a bunch more things that you can do with acetylide ions next term when we get into the chapters on carbonyl chemistry in Organic 2, Chem 228. But we'll cover at least one today, one very characteristic reaction of these acetylide ions that actually will also make a very nice segue into chapter 11, which is where we're going next. Good, and having dispatched all that, whatever time is left in class, I would like to use to give you at least some pointers on what synthesis problems are and how to solve them, and try to at least lay down the basics of what you need to know in order to be able to solve a synthesis problem successfully. You'll have run into them in the OWL assignment, of course, and you'll have noticed them, I'm sure, on my previous exam, my old exam that I posted on eCampus. There also are some other synthesis problems that I posted on eCampus, I believe anyway, should be there with the class notes. And I've posted the answers to those as well. And also, while I'm on the topic, just a reminder, I will not be posting an old final exam. That's a departmental thing. That precedes me having come here. But the other organic professors also traditionally have not posted an old final exam. We figure we're doing enough just posting old hour exams. Good, so I think that's all I need to say by way of a preamble. So we've already said that the idea is if we have a terminal alkyne, which is a compound of this type, and R can be pretty much anything, at least as long as it's not going to react with a strong base. Certainly R being any alkyl group will be just fine. But if we treat a terminal alkyne with a strong base, we will deprotonate the terminal alkyne and get this acetylide ion. And one good choice of base is sodium amide, NaNH2. And I want to be, ooh, I forgot my minus sign. Shame on me. But I want to be very clear what we're talking about here, because you know me by now. I'm not going to find it acceptable that you just memorize an N and A, an N and H, and a 2. I want you to understand what this species is. And in fact, it's the conjugate base of ammonia. So I think that even on the face of it, sounds like we're talking about a really strong base here. The sodium cation is nothing more than a counterion, right? I'm hoping that by now you guys can recognize after Gen Chem, when you're looking at an ionic compound, in general, you look for a metal combined with a non-metal. So this is going to be an ionic compound. And I feel your pain, having taught Gen Chem as well as organic chemistry. I think one of the hardest things to learn in Gen Chem 1 is ionic compounds. And the main problem with them that would have been avoided if only way back when they made these decisions, they had decided to write something like NaNH2 like this, with a plus and a minus to show the cation and the anion. So I probably said, 3,000 or 4,000 times in my career, at least as far as teaching Gen Chem, that when it comes to writing the formulas of ionic compounds, the charges are still there, we just don't write them. Why, I don't know. That would have made everything so much easier. But the sodium cation is just a spectator ion. I certainly do not ever want to see any sodium-nitrogen bonds. I want everyone very clear that you're looking at this anion, which is the conjugate base of ammonia. And sometimes what I like to say, some people find it a little funny, most probably don't, but sometimes what I like to say is, if you absolutely have to draw the sodium ion, or your face is going to fall off or something, please at least put it in the next county somewhere, so that I understand, I'm exaggerating here, but that I know that you're very clear that this is an ionic compound and the sodium ion plays no role in the chemistry here. So what we have then is the conjugate base of ammonia. We know that ammonia is amphoteric, like water, meaning that it can act as either an acid or a base. And so this is what you get when you pull off H plus from ammonia, which of course would require an even stronger base. And there are other bases besides this one that will pull off that proton for us. We'll learn some of them later. One that we'll meet next term, for example, is LDA, which is lithium diisopropylamide, which instead of a sodium salt is a lithium salt. And it basically looks just like NH2 minus, except you'll replace both hydrogens with isopropyl groups. That's another very commonly used strong base, and we'll meet that next term. And there are others as well. There are bases still stronger than this that would also work in this context. But first, I want to clarify why it is that we're using this compound and not some other base that might come readily to mind, like, I don't know, hydroxide. Isn't that usually the first base we think of? It's kind of the go-to strong base, almost to the point that one could almost think, coming out of Gen Chem, that it's the strongest base there is, which of course it is not. But even more particularly than that, one could almost think that it would be good for any application. And that's not true. This is an application that hydroxide is not a strong enough base to do this job for us. We need to go with something stronger. So how can we know that? What do we need to know in order to understand that? Well, what we should always do when considering base strength is also consider acid strength of the conjugate acids of these species. And I think you'll agree that I've sort of set up a series here of these three anions, and we have here their conjugate acids. And again, I don't think it's necessary for you to memorize exact numbers. I didn't look these numbers up before I wrote them down. But as I recall, ammonia has a pKa somewhere in the mid to high 30s, 36, 37 rings a bell. Terminal alkynes turn out to have a pKa generally in the mid to upper 20s. Somewhere in the 26 to 30 range is pretty typical. And water, of course, mid to high teens, round and about 16 is the pKa of water. And so remember what pKa means. Remember that the acid gets stronger as the pKa gets lower. That's due to that tricky minus sign. In pKa is minus common logarithm of H3O plus constant, or rather of the acid dissociation constant. That's due to that minus sign. So water is the strongest acid in this series. And remember that base strength goes opposite to conjugate acid strength. That means that of these three, NH2 minus is the strongest base and OH minus is the weakest base. And that makes sense, I think. Why is this the strongest base, but its conjugate acid the weakest acid? Well, I think that's something we can understand. And I think that's something you need to understand in order to learn this aspect of today's material correctly. You need to understand this in order for it to make any sense to you at all. Again, you know me. I'm not going to accept you just memorizing an NNA, an NNH, and a 2. That's not an adequate level of understanding of this material. But I think you can handle this. Do we have a base in the reaction at the top of the page? Well, I just drew a generic base over here. And I just point out here that, you know, NH2 minus is a good choice with the base over here. So here I'm being very generic, and then I'm pointing out that this is one good choice of base. And there are others. We'll learn about other really strong bases that will do the job also. But this is certainly good enough. But anyway, I think you'll agree if NH3 is the weakest acid of the bunch, then shouldn't its conjugate base be the strongest base? If this of the three acids is the one that least wants to give up H plus to make the conjugate base, doesn't it make sense that this conjugate base is the one that most wants to get that proton back and go back to the conjugate acid? This is how you need to be thinking in order to make sense of this. Meanwhile, in this series, water is the strongest acid. And normally we don't think of water as being an acid. And indeed, it's not a particularly good acid. But compared to the other two, it's better than either of the other two. And so if this is the strongest acid, if this is the one that is most willing to give up H plus and make the conjugate base, well, then that conjugate base is, of the three choices, the one that's happiest to hold on to the minus charge and is most willing not to take back that proton and go back to the conjugate acid. So since we have this sequence here, and again, let's not forget that the pKa scale is logarithmic. So each time we move along here from 36 to 26 to 16, we're getting 10 orders of magnitude more acidic here. So what this tells us is that OH minus is nowhere near strong enough to pull off the proton from a terminal alkyne in any reasonable concentration. Yeah, it may pull one off here and pull one off there, but certainly nothing in nowhere near a quantitative amount are we going to pull that proton off. That's why we need the conjugate base of something with a higher pKa than that proton in order to pull that proton off in anything approaching quantitative. And so that's why this is a good choice of base, sodium amide, we call it. Usually the solvent is going to be liquid ammonia, which we've already met, and we'll go over that shortly. Question back there. Well, not all of them. Water and ammonia are, but not the alkyne. Right, because water and ammonia are amphoteric. So there are H3O plus and NH4 plus. We can talk about the pKa's of those, but I don't know that it's going to enter into the discussion here. I mean, you're right. I just don't know that it enters into the discussion because those species are not involved. Let me think now. H3O plus, I would have to think, is a stronger acid. The question is about the further conjugate acids of water and ammonia. But I would think H3O plus is a much stronger acid than NH4 plus. So I don't know how consistent that is with the other ones. I guess it's the same, right? Because NH4 plus is pK of what, 9 or 10, something like that? And H3O plus, I'm pretty sure, is like 1 or 2. It's really down there. So I think that's true, but I don't think those species enter into this particular domain. But I mean, what you're saying is still right. Good. Other questions then? All right, so now that we have that down, now that we understand what is the species that we're dealing with, that it's the conjugate base of ammonia, And we understand why we're picking it as to maybe hydroxide or something other like that. It's because a base like this, as strong as it is not strong enough to pull the proton off of a terminal alkyne. So that's fine. The only question after this is why? Why is a terminal alkyne this acidic? I'm hoping that the pK of 26 jumped out at you. That's really low for a hydrocarbon. We don't normally find CH bonds being particularly acidic. And you know, you can compare that, for example, to a CH bond connected to an alkene, and here your pKa is going to be maybe 40 something, give or take. And of course, a CH bond connected to an alkane, an sp3 hybridized carbon, that's going to be even higher. That's going to be through the roof, like 60 or even higher. So something unusual is going on here. Why is this proton so much more acidic to the tune of, 15 orders of magnitude more acidic or more than an alkene, and like, what do you want to call that? 35 orders of magnitude more acidic than an alkane? Something unusual is going on here. And I think you need to understand that. I think you need to know this in order to make any sense of this material and why terminal alkynes are special in terms of acid-base strength. Yes? Good question. He's asking why can't we use the conjugate base of an alkane to pull the proton off? You most certainly can. That's another one that would work. I don't think you're going to find very many conjugate bases of alkenes that are readily available. But certainly something like butyl lithium is cheap and commercially available, and you can certainly use that to deprotonate a terminal alkyne. But I'm just focusing on sodium amide because it's the one that your book talks about here. But absolutely, if you were to put that down as your base, butyl lithium, fine, totally acceptable. But we don't need to go that far. That's really using a sledgehammer. And one basic principle of organic synthesis that I've learned over the years is, in general, we use the smallest hammer we can get away with, and we only go for the big one if we have to. But in terms of would it work in principle, absolutely. So all that being said, let's go back to comparing our hydrocarbons and the pKa's of those three types of hydrogens here. And it's all going to come down to the hybridization of the carbon to which that hydrogen is attached. So I think you'll agree that this carbon is sp hybridized, as is, by the way, the carbon on the acetylide ion. And that carbon certainly will be sp2. I don't think anyone will argue with me here. This one will be sp3 hybridized. And that's going to turn out to make all the difference. But I think it's critical to understand why that makes all the difference. So let's compare those three hybridizations. And let's think all the way back to Gen Chem in terms of how these things come about. How do we get these hybrid orbitals? Well, I think you'll agree, in order to get sp hybrid orbitals, we mix one s orbital and one, well, that looks bad. It looks like I'm talking about the first energy level. Let's say that it's s plus p. And so we're going to mix those two orbitals, and we're going to get two new orbitals, two new sp hybrid orbitals. Right? Nothing unusual there. And so what that means is that, I'm trying to think how to write this. What that means is, in these two new sp hybrid orbitals, each of those sp hybrid orbitals is 50% s character. That's going to turn out to matter quite a bit in a moment. But I want to be sure that everyone's clear in how I got that. I think you'll agree, if we mix these two orbitals to get sp hybrid orbitals, well, you've got an s and a p mixed together. A total of two orbitals, one of which is an s orbital, gets us 50% s character, 1 out of 2. Make sense so far? Well, if we continue with that logic, if we now mix together an s orbital and two p orbitals, then we're going to get 3 new sp2 hybrid orbitals. And let's think for a moment about sp2 in exactly the same way. If we've got 3 orbitals mixed together, one of which is an s orbital, then each of those sp2 hybrid orbitals should be 1/3 s, right? 1 out of 3. We'll say 33% s character, certainly close enough. S character, sorry. Character. Good. And what about sp3? Well, same idea. We're going to mix an s orbital and 3 p orbitals, and we're going to get from that 4 new sp3 hybrid orbitals. That's going to make our tetrahedral shape. And each one of those sp3 hybrid orbitals, out of 4 orbitals mixed together, it's 1 s and 3 p's. So out of the 4 orbitals, you've got 1 s orbital in the mix. That means each of those hybrid orbitals will have only 25% s character. And that's what's going to turn out to make all the difference here. Why? Well, let's think for a moment about what an s orbital looks like. It's, of course, spherical. Maybe not my best sphere ever, but it's spherical. And I think you'll agree with me that in terms of distributing minus charge or electron density, in terms of reducing the amount of electron-electron repulsion between any electrons that we put in that s orbital, I think you'll agree it doesn't get any better than spherical. That's the best distribution of minus charge or electron-electron repulsion. You can't get the minus charge any further away from itself, so to speak. You can't distribute that any better than on the surface of a sphere, any other shape than that. And you'll be bringing the negative charge closer together than you really need to. So the sphere is the best way for distributing negative charge. So good choice for distributing negative charge or electron-electron repulsion. And why does that matter? Well, I think you'll agree that on our acetylide ion, we've got a full minus charge. There's an electron pair sitting in that sp hybrid orbital. And so the better we can do at stabilizing that minus charge, well, the happier the corresponding hydrocarbon, the conjugate acid, will be to give up that proton and make the minus charge. So that's what s orbitals look like. What about p orbitals? Well, we know they're sort of dumbbell shaped like this. And I think you'll agree this is not a good choice for distributing minus charge. Here you're bringing negative charge closer together than you really need to, especially as you approach the nucleus. There's going to be some electron density there as well. And you're bringing it very close together. You're not spreading it out like on the surface of the sphere. So we're distributing minus charge. So what we're learning is the more S-like the orbital is into which we're putting the minus charge, the better off we are. And now you can see sp hybrid orbitals have 50% S character. That's the best we can do here. The others have less S character, 33% S, and so the remaining 67% would be P character here, and the remaining 75% would be P character in an sp3 hybrid orbital. And that, I think, fully explains this sequence here. That fully explains why alkanes are so non-acidic, because you're asking the carbon atom to put that lone pair into an sp3 hybrid orbital, which is only 25% S in character, and not at all good at reducing the amount of electron-electron repulsion by spreading out the minus charge. And then sp2 slightly better, sp best of all. Now we've got 50% S character, and so this is the best we can get, at least, in terms of spreading out the minus charge or reducing electron-electron repulsion. And that's why, of these three types of hydrocarbons, terminal alkynes are the strongest acids. Again, by a rather dramatic amount when you compare to the other ones. Now, I know I'm really belaboring this, but I think you need to know this in order to understand this part of the material. It's not going to be enough to memorize NaNH2 to the thing and pull off the, that's not going to be enough if you don't understand why. Another question back here. Well, but he's saying H2O is sp3 hybridized. Indeed it is, but oxygen is quite a bit more electronegative than carbon. So, and as you would guess, nitrogen is in between the two. That's going to be somewhere in between. So that's why water is a pKa of 16 and ammonia 36. And so now if you go to the alkane at 60, that kind of makes sense. Let's see now. Question chat. Wouldn't the alkanes, alkenes, and alkynes all be expected to lose the proton? Yes. Are you saying the sp hybridized carbon would be most likely to lose? Yes, that's exactly right. And the reason is because the sp hybridized carbon has the best stabilized anion compared to what you would get if all of these lose the proton. So yes, if you want to see, if you want a visual aid on what those anions look like, absolutely we can do that. Yes, they would be expected to lose the proton. But the one that does the best at it is the one with the most S character in the orbital, holding on in the orbital containing the minus charge. So that's going to be the sp hybridized carbon. But yes, basically, my answer to your question is yes. I think that's exactly right. Oh, yes. I don't know that that matters as much because those electrons are held in a different orbital. We're just comparing the orbital that's holding the minus charge in it. And so, because if we start comparing other things, then we're not comparing apples to apples. I think this is the best apples to apples comparison in any case that we can make. So, so that's what I would say in answer to that. Good. Good. So, like I said, I hope you'll pardon me for belaboring this point, but I really feel it's necessary for you to understand this, as opposed to just diving in and saying, here, this pulls off the proton, makes a thing, learn it, live it, love it. I just want to make sure that everyone is very clear on why all this is happening, why we need a base as strong as sodium amide or something stronger still, and why it is that we're able to pull that proton off relatively easily in the first place, as compared to alkenes and alkanes. Good. Other questions then? I always feel bad for the people that are behind me. All right. Now, with all that being said, I think now we're ready to consider. Let's see. I have until 12:50. Now we're ready to consider what we can do with all this. And the idea is that we can use sodium amide to pull the proton off of a terminal alkyne, and then we can use that terminal alkynate ion or terminal acetylide ion as a nucleophile. And there's thousands of electrophiles that we can treat it with. One that we already understand pretty well is alkyl halides, especially primary alkyl halides. So to give an example, well, actually, I won't give an example. I'll give a generalized case first. So if we started with some terminal alkyne, doesn't matter which, and we treated this with sodium amide in, again, the most common solvent is liquid ammonia. There are others that would be okay. I think diethyl ether would be fine. Then we're going to get the acetylide ion. Actually, let me make this R1 now that I think about it, because I want to use an R2 over here. For my second step, I would want to use an alkyl halide, preferably primary. Whoops. So we'll say R2 CH2X, and we'll say X can be chlorine, bromine, or iodine. I don't know how well fluorides would react. Probably not so great. So what's going to happen here is something we understand very well. And so both of these mechanisms, I think, are something we can understand. Here we have our NH2- ion pulling off that proton. and making the acetylide ion, just an acid-base reaction. That's something we understand very well. In the second step, we have the acetylide ion acting as a nucleophile, and that's going to attack the carbon that bears the halogen leaving group, the halide leaving group, and will form a new carbon-carbon bond. And I forgot again, I just want to rewrite this in color. Let's make the alkyl halide red. Oops. Just killed something I didn't mean to kill. I just want to make sure that everyone has a good visual aid here. R2, CH2 halide. Good, and I think we will break that carbon-halogen bond. We'll form the stable halide ion. And I think you'll agree we're going to make a new carbon-carbon bond, looking something like this for our product, CH2R2. And so what we've done here is we've made a new carbon-carbon bond. And as I think I've pointed out before, any time in organic synthesis you can make a new carbon-carbon bond, that's money in the bank. Big sign. Because that means that you can convert a smaller compound into a bigger one, or a simpler compound into a more complicated one. That's big for anything that encroaches at all upon organic chemistry. Any of your pharmaceuticals type fields, anything like that. So to give an example, I think we have time for maybe one example. Let's say that we took 1-butene and treated it with sodium amide and liquid ammonia. You don't really have to put one in this case. As long as you use separate arrows, it's clearly implied. Well, we can understand that. That's going to get deprotonated, just as we said, by the NH2 minus ion. And yes, you will get a molecule of ammonia out of that. There's already plenty of ammonia around. And you'll get that acetylide ion. And now let's say that we treat it with benzyl bromide. Well, that's going to attack the CH2 and expel the bromide leaving group. In chapter 11, which is coming up next, we'll learn that this is called an SN2 reaction, for substitution nucleophilic bimolecular. And that's why it's best, for best results, you want that alkyl halide to be primary. Secondary might work to some extent. Probably you'd get kind of a low to moderate yield. Tertiary alkyl halides are right out. They will not work in this type of reaction. The best ones are your primary alkyl halides. I think you'll see we will get, you can write CH2PH, you can write CH2C6H5 if you like that better, or you can just draw out the benzene ring. All three are fine. So you would get a compound of this type, again with a new carbon-carbon bond. Good. Yes? No, the question was, would this work with vinylic halides? No, that the carbon-halogen bond is too strong in those. And we'll learn, I think, why in chapter 11. But this works best of all with primary alkyl halides, maybe secondary, and certainly not tertiary or vinylic. So you need that carbon to be sp3 hybridized that has the halogen on it. And we'll learn why in chapter 11, I would say. Good, other questions, and which is on the same unit, by the way, right? The next exam is 9 and 11. Okay, well, that leaves me 7 minutes to discuss organic synthesis. I had about 10 minutes to discuss it in my previous class, which makes me think I'm probably going to put up the previous class's lecture because I had a little more time for discussion here. And I always wish I had more time to talk about organic synthesis, but I at least want to kind of lay out the basics for you so that you have some idea of the tools that you'll need in order to solve organic synthesis problems. But an organic synthesis problem basically looks like the following. In general, you're given one or more organic starting materials, and you're then tasked with, in 2 or more steps, so it will never take just one step, in 2 or more steps, could be 3 steps, 4 is kind of pushing it. 10 is too many, probably. But certainly more than one step, you're expected to make the given product out of it. And a couple of things, again, I just want to make sure that you understand the basics of what you'll need to know in order to be able to solve these. You've got examples of synthesis problems on my old exam. You've got other synthesis problems to practice that I put on eCampus. And then there's, of course, the OWL assignment. But one thing for starters, the thing I need to say first, in order to be able to solve synthesis problems, you must know all your reactions, absolutely cold, backwards and forwards. That's non-negotiable. If that's not there, then you cannot solve synthesis problems. And so please refer back to my class notes so that we're clear on what it means to know a reaction. And if there's some brushing up you need to do after this last exam, well, there's certainly time and space for that. That's fine. But that's got to be there. And by the way, you never get to forget any reactions. This course is cumulative over the whole term. And an Organic 2 will expect that you still know all the reactions from the first term, since we're going to use a lot of those to explain some of the later reactions. So that's the first thing. The other bit of advice I could give you, and all this is in my class notes, by the way, the other bit of advice I can give you is that it's helpful to think both backwards and forwards. In other words, looking at your starting material and saying, okay, what functional groups are here that I know reactions that can act on those functional groups, and what can I turn those functional groups into with one step? And also looking maybe at your product and saying, okay, what kind of precursor could I have had to this using a reaction that I know that might give me a molecule that looks a little more like my starting material? So that's one bit of advice I can give you. Learn to think both backwards and forwards. You can feel free to burn that candle at both ends. Another thing, by the way, that's very helpful is to count carbons, right? You want to make sure that you're not creating or destroying matter. We do not violate the law of conservation of mass here. So I think we have time for at least one example. I'm hoping two, but hopefully at least one. One example of a synthesis problem, let's say that we're given pentine, one pentine, and we're told we need to convert that to this compound. That would be a very fair question on the exam. Might even be a little on the easy side, but that's okay. So what I'm thinking when I look at this is, first of all, I notice I have only 1, 2, 3, 4, 5. I got 5 carbons in the starting material. In the product, 1, 2, 3, 4, 5, 6. So I've got 6. So that means I've added a carbon somehow. So that's the sort of thing you need to clue in on. But let's say that you're told you can use 1 pentine in any alkyl halide you like. Let's say RX. And besides that, of course, any inorganic reagents you like in order to make this compound. Well, when I look at this alkene, and I notice that I'm starting with an alkyne, one thing that the natural thing to ask yourself is, do I know a way to turn an alkyne into a cis alkene? And I think we do. We learned that the other day. We learned that if you take the corresponding alkyne, which would look like this, and you treat that with hydrogen gas in the presence of Lindlar catalyst. I'll just write H2 in Lindlar, that's fine. Well, then it will convert the alkyne into the cis alkene. So this is the level that you have to know all your reactions on, literally backwards and forwards. So that's fine. That gets us part of the way there. And then the next question to ask would be, well, do we know a way of converting this alkyne into that alkyne and adding that carbon on? And I think we do. I think we just learned it. What we would do is we would first deprotonate that alkyne with sodium amide and liquid ammonia. And then we would want to add a methyl halide. And I'll just let you know, in real life, the methyl halide we would always choose would be methyl iodide. If you put CH3Cl or CH3Br, it's fine, it's acceptable. But in real life, we would want to use methyl iodide. Why? For the simple reason that methyl iodide is a liquid at room temperature, and the other two are gases, and they're just that much more difficult to dispense and deal with. But they would still work in theory. And so when we get the anion here, that's going to attack the methyl iodide and put the methyl group on. So there is one possible synthesis. And a couple other pointers that I want to be sure to give you. One thing that I think is worth knowing, and maybe even ending on this, is with synthesis problems, there's almost always multiple correct answers. And I'll even let you know this. On pretty much every exam that I've given synthesis questions on, whether here or at my previous school, there's almost always at least one student, in classes this size, it'll probably be a few students, who come up with a synthesis, come up with something that I would never have thought of, but it would work. And so I accept it, I give them credit. That's not rare on exams that have synthesis problems. So take a look at the synthesis problems that I've put on eCampus. I've given the answers also, and they're not the only correct answers, as I just said. Take a look at my old exams. That will also give you some ideas. Certainly work with the OWL assignment. And I would even say, if you're working on any of these synthesis questions and you come up with another way to do it and you're not sure if it's right or not and you want to bring it to office hours, please do so. Be happy to look at it for you. Let's say that we were given this starting material, cyclohexanol, and we wanted to convert it to this cis diol. Well, of course, we can't do that in one step. I think we're going to need at least two. So the question then becomes, does this cis diol look familiar to us? Do we know how to get cis diols like this? I think we do. I think we get them by treating an alkene with osmium. So osmium tetroxide in tert-butyl alcohol or pyridine, doesn't really matter which. And then as a second step, we need a reductive workup, which is sodium bisulfite, NaHSO3 in aqueous. So that will convert this alkene to that cis diol. And now we just need to ask, can we convert an alcohol to an alkene? Well, certainly we can. And you can do it in one step or in multiple steps. I would say that if we treated this with a strong acid like sulfuric acid, or phosphoric acid would also work. Phosphoric acid is fine. Well, that will cause elimination of water to go from the alcohol to the alkene. We discussed that in chapter 8, I believe. Could also have been in 6 and 7, when we talked about how it is how we make alkenes. So that's one correct answer. You might come up with others. There are other reagents besides osmium that will make the cis diol for us. We learned about them too in chapter 8. So that would certainly also be fine. So that's the idea behind doing synthesis problems. Like I said, I wish I had more time to talk more with you guys about that. The best thing is to get in there and practice. So I have some other examples on eCampus. You've got my old exam as well, plus OWL. So with that, I am definitely out of time. So have a good weekend. I will see you all on Monday.